If you've ever attempted to use a TV outside, you'll have probably been disappointed because you just can't see anything on most TVs when used in such a bright environment. However, with a little bit of ingenuity, it's possible to convert pretty much any old or in some cases broken TVs into ultra-bright outdoor monsters that can be viewed easily, even on the hottest summer days. Perfect for watching big sports events with friends or having a barbecue gaming tournament. And if the weather lets you down, it's of course going to be weatherproof too. Now, as you can imagine, the build process for something like this is pretty interesting in and of itself. But it's been made even more interesting by the fact that you guys have voted for me to keep the cost as low as possible, which has meant for some really interesting workarounds around keeping it cool. That's right, this is a water-cooled TV. More about that in a bit, but for now, let's get building it. This video is sponsored by KiwiCo. More about them later. While it is possible to use old but otherwise working TVs for the backbone of this project, it actually makes a lot more sense to use a faulty one, as these can often be had for next to nothing. Despite this one's obvious image fault, it's a fairly new unit featuring 4K capabilities, and as the fault is to do with its backlight rather than the LCD layer itself, it's perfect for utilising for this project, especially as reusing it will prevent it from going into landfill. And as you may have guessed, the first job is to open it up. As most TVs run off mains voltage, it goes without saying here that it needs to be unplugged for this, though like everything, if you copy anything in this video, it's all done at your own risk. Continuing the strip down process should reveal a PCB, and this will be needed later so can be safely put to one side for now, as we are first going to focus on the LCD layer itself. You see, in an LCD TV, this panel is actually what produces an image, but not directly. It works by selectively blocking out light that's produced by a backlight layer, a bit like a shadow silhouette. It's this backlight functionality that can be exploited to make the TV super bright for outdoor use, but there are some serious hurdles to overcome before this can be achieved. Now, as you can see, the original backlight layer on this TV can be seen underneath the LCD panel, which is lit up by some LEDs from behind, a few of which are presumably faulty, hence the dark corner. Now, coming back to the LCD layer, it's very flexible and fragile, so wouldn't last long if exposed to the elements outside, and as a result, it needs to be reinforced. I'm going to use a sheet of glass for this, and again being cost conscious here, I've acquired mine by reusing the top from an old coffee table. This is ideal as it's toughened, making both the build process and final TV much safer by its use, and a couple of other alternatives to this could be glass from a shower refit, or any tempered windows that are being replaced. Now, mounting the panel directly to this glass is fairly straightforward, as it can be simply glued in place with some UV reactive glue. After masking off the panel and its delicate ribbon cables, this glue can be added straight onto the panel's front surface, and the glass carefully lowered on top. One thing to notice here is that as soon as the glass touches the glue, it instantly gets darker, as internal reflections are eliminated, with the glass and LCD panel becoming one. This should increase the image contrast and make the TV much easier to see when in use, as well as provide a lot of structural strength. Unfortunately though, many air bubbles have been introduced into the glue, but thankfully it's pretty easy to get rid of them by simply pushing gently against the underside of the panel with a leather strap in order to squeeze them out one by one. Now, this glue only sets when exposed to UV light, but as you can imagine, curing such a large surface area with a single UV torch would take rather a long time, so I left mine outside to set in the sun's natural UV rays. After cleaning up the edges, it's now extremely solid and looks quite neat, though with the outer perimeter being clear, the backlight will be visible through it and be pretty distracting, so I've decided to mask off the panel and spray this perimeter from behind with Plasti-Dip. This covers it in a layer of rubber-like paint, and with it being on the back of the glass, it should look solid and very dark from the front, but we'll check that out in a bit. For now though, the last thing to do is mount the original diffusion sheets in place, as these are important to keep the final image looking even. This whole process makes the panel extremely secure and safe, but being mounted to a sheet of glass means that there's no chance of it fitting inside the original TV's casing, so we'll have to make our own. This casing can be started off with some aluminium U-channels, and as you can see, these have had some miter joints made in them so that they fit around the perimeter of the glass quite nicely. However, before fixing these in place, it's necessary to make some larger additional panels that can screw into these U-channels to make the sides for the new casing. When mounting these together, it's important to make a watertight seal between them to keep out any water ingress, and I've found that using CT1 glue is ideal for this job as it sticks to aluminium extraordinarily well. This same glue can be also used within the U-channels themselves to stick them permanently to the glass in a way that makes them watertight. These side panels extend quite a bit below the bottom of the glass, and that's because this area will house the electronics as well as a cooling radiator, and so the front cover that fits here needs to have various vent slots made in it for plenty of air through flow. These slots were created by simply drilling lots of holes and then bridging them together to make ovals. They only cover the area on the right though, as the intention is to use the leftmost side to house the electronics, starting with the TV's original control board PCB, which can be mounted in place with some pillar supports. Underneath all this, a bottom panel can also be added, which as you can see features various port extensions for HDMI and audio and can be plugged in along with the display's link cable. When it comes to the power cable though, it's vital to make sure that a grounding tab is connected directly to the aluminium, as this grounds the entire outer casing, which is really important for safety. Now, as this board does handle mains level voltage, using some more pillars to mount another sheet of aluminium above the top side is a good idea, as it locks everything in, making a nice grounded enclosure for safety. So with that done, things are definitely taking shape, and the last thing to work on is the backlighting system, which is where this build gets extremely unique. As you'll remember, the original backlight consisted of an array of LEDs, and while they are powerful enough to light the TV up in an indoor environment, they're just far too dim to permit the original TV to be viewable outdoors. So we need a far brighter alternative, and there are lots of options here on the table. Option 1 is the easiest and cheapest, which is to simply use LED strips. The LEDs on these are spaced much closer together than on the original TV's backlight, and so would be far brighter for the full screen surface area simply due to having a greater density. The idea here would be to stick several rows of them onto an aluminium backplate and then solder them together in parallel. This can make an extremely bright backlight panel for as little as $50, and it should illuminate the display about 4 times more brightly than it was originally, which is a pretty big performance boost considering the cost. With a slightly bigger budget though, it's also possible to use these giant cob LEDs. Buying enough of them to make a large enough grid for the backlight is about 3 times as expensive as using the LED strips, but the resulting brightness should be over 12 times brighter than the original TV, so it should be easily viewable outdoors. Despite these budget options being on the table though, I'm personally going to use some aluminium substrate LED panels that I already have to hand. They are somewhat overkill as they're really intended for high-end indoor lighting or studio use, but I'm really curious to see what kind of effect they'll have on the colour quality of the final display, as they feature an extremely high CRI of 95, and I have a feeling that this will affect the TV's colour output substantially, but we'll have to wait until later to see the results of this. Now, just like the LED strips, these panels can be mounted onto a backplate, only this time using thermal compound in between them to aid in heat transfer. As mine don't feature any mounting holes though, I'm clamping them down using some nuts and bolts along the edges. So with that done, it's almost ready to be mounted on the inside of the TV, but there are a couple of things to do first, starting with adding some U-channels around the rear perimeter. These add a lot of rigidity to the panel as well as making for great mounting points, but they're also essential for cooling, which is a hint about what's to come. Another thing to consider before this gets mounted in place though is how to power all of these lights. With the LED strip version, the power draw would be about 500 watts, so a good option for powering them is with a recycled server power supply. These can be had very cheaply online and are able to deliver very high wattages. This 750 watt version, for example, was less than $10 and outputs a stable 12 volts, so is perfect for using with LED strips. To turn them on, they do need some extra wiring, but this is usually fairly easy to do, and I'll soon have a video up about this topic specifically for those of you who are interested. Once they are powered on, the LED strips just light up, so you can see that this method is extremely cost effective and simple to execute. The Cobb LED version is pretty much the same, but as they use a total of 1600 watts instead of just 500, splitting them into 3 independent rows is required to spread the load over 3 power supplies. For my build though, I've made things a bit more complicated for myself, as the LED panels that I'm using require 48 volts rather than 12, so I'm having to use some voltage boosters to achieve this higher voltage. There's just enough room for these above the TV's control board, after which the main panel can be lowered down and screwed in place with the LEDs facing the back of the TV screen. Now it's tempting to give it a try at this point, but there is one major thing to tackle first, which is cooling. You see, despite LEDs being comparatively efficient, they still throw away over half of their input power as heat, which can be quite problematic when there are so many of them, as they'd fairly quickly heat up so much that they'd burn themselves out. The wattage of the LED strip version is low enough that it may be possible to keep them cool by just having some fans underneath them to provide a flow of air over both the front and back of the aluminium that they're mounted to. However, with both the Cobb version and my version, there's far too much heat to be dealt with this way, so it needs some extra help. Normally, this help would be provided by some aluminium heat sinks, but the sheer mass of this much metal would require a spend of over $300, which completely negates most of the cost-saving measures taken so far. Taking this dilemma to a poll, I pitted the option of this conventional but expensive method against a very unconventional but still functional idea. And well, pretty much everyone chose the latter, so things are about to get weird, as I'm going to be using water to take heat away from these LEDs, which then in turn gets cooled by a radiator. Car radiators are ideal for this, as they can be super cheap or even free if you get one from a scrapyard. Just clean it up and leak test it first, and it's good to go. Getting the heat from the LEDs to the radiator though is the secondary reason why U-channels were mounted to the perimeter of the LED panel that I hinted to earlier, as thanks to using CT1 glue and providing a rubber gasket around the neck of each bolt, the entire back side of this is completely watertight. The idea isn't to completely fill it up though, as that would get heavy fast, so instead we'll be doing something a bit more efficient by utilising a variety of plumbing bits. The first couple of these are for an inlet and outlet port, with the inlet being joined up to a long tube with a T-splitter at the top. The pipes that get joined up to this T-splitter need some small holes drilled into them at even intervals, and then a cap at each end, and once they're in place you can perhaps see where this is going. In order to force the water up into this pipe though, it's necessary to install a cheap submersible water pump on the outlet port, with the idea being to force water from this pump into the radiator, after which it returns up the pipe and then runs down the back of the aluminium backplate, cooling the LEDs in the process. Before it can get attached to the radiator through some tubes though, a cover needs adding which features several fans to move air through the radiator. To aid in rain rejection here, I've added some little plastic fan filters, which do a great job of catching any water droplets and allowing them to harmlessly trickle away. And with that, the tubes can be hooked up to the radiator and the protective film peeled away, making it almost ready to use. So with it all plumbed up, the last thing to do is add some kind of back panel onto this chamber. I'm going to be using acrylic, as it's quite cheap at the moment, and as you can see mine's still got the blue film on, which is why it's blue. But before I do that, I'm actually going to use these U-channels as handholds to take it outside, because I've got to take it down 2 flights of stairs before we can use this thing, and it's pretty heavy. But before I get on with that, and then we can fill it up and give it a test, it's time for a quick ad from this video's sponsor, KiwiCo. KiwiCo make fantastic hands-on projects for kids of all ages, focused on the topics of science, technology, engineering, art and maths, with a goal to teach some seriously in-depth ideas in a practical and fun way. This Tinker Crate, for example, teaches the concepts around the forces of friction and how it can be utilised to create some really cool friction climbers that utilise, well, friction to climb. Each project contains everything needed to make it, with detailed, kid-friendly instructions and an educational magazine that's filled with extra content to learn even more about each crate's theme and how it actually works. I'm personally a big fan of how KiwiCo brings these concepts to kids in fun and creative ways, and I've said many times that doing kits similar to these when I was small is one of the reasons that I developed an interest in designing and building things, so who knows where it can go in the future. They offer 8 subscription lines catered for different age groups, with shipping available to over 40 countries. On top of that, they've got a great offer on at the moment where you can try your first month of selected crates completely free. And you can take advantage of that offer by going to kiwico.com/DIY perks, which you can also find linked to in the description. So again, to get your first crate completely free, visit kiwico.com/DIY perks. So with the unit now outside, it's time to seal it up with the back panel. Instead of using CT1 glue here though, which would bond it permanently, I'm using standard silicone, which while still making a watertight seal, can be peeled away if maintenance is ever required, and the strength is aided by many small screws, provision for which I made earlier. Now whilst this dries, it's a good opportunity to sort out some kind of stand. I'm just using some U-channels for this, and to aid their rigidity, I'm using some nylon to make a cross on the rear 2 legs so that it prevents side-to-side wobble, and a single line between the rear legs and the front legs to stop them from splaying apart. Now rather annoyingly, it just so happens to be the windiest day of summer, with a really blustery breeze blowing everywhere. So as a precaution, I added some side lines as well as pinned each leg to the floor to lock it down, which is essential to do anyway really, as it prevents it from falling over, particularly if you have pets about. So as you can see, it looks really impressive and unique. Before it can be turned on though, some water does need to be fed into it for the cooling system. As this takes quite a while to do manually, I used another small water pump to push the water inside more quickly. Eventually, once the radiator's full, the water begins to run out of the TV's own pump and fill up the internal chamber, which essentially acts like a reservoir, and once it's above the pump's intake, it's primed and ready to go. As you can see, I've hung the power supplies on the back here, as there's no room for them internally, and I don't actually mind this, as it allows me to use them for other projects as well as keep them inside when the TV isn't being used. Now for a sound system, I'm using some bookshelf speakers for extra volume, with a table behind everything to keep any of the devices I want to plug in out of the way. So as soon as I plug this in, we should see a picture. So are you ready? 3, 2, 1. Whoa, yeah! Look at that! That is bright. Listen to the water cooling as well. Whoa! Yeah, that's definitely working. Wow, that's going to keep the LEDs really cool. That's perfect. As the water flows down the back of this panel, it pulls heat away from it, where it's then expelled by the radiator. Heat is able to escape the inside chamber as well, with the fans also partly encouraging the air to be pushed out of some top holes so that the LCD panel itself doesn't overheat with all the light hitting it from behind. One of the things that struck me with this final image is that the colours are so vibrant, and I think this has to do with the new LEDs extending the display's colour gamut way past the rather bland sRGB it was originally. But unfortunately, I can't get any exact measurements for this, as the display is just so bright that it actually blows out the spectrophotometer I was planning on using. This means that getting a precise brightness measurement is out of the question as well, but comparing it to my smartphone, which has a maximum display brightness of 1000 nits, it easily beats it and by a significant margin. And it wouldn't surprise me if the TV was now hitting at least 2000 nits in brightness, which is pretty wild. Look at how bright this is! That's easily visible, like this is basically as bright as it's ever going to get, yet you can easily see the television, and I think that's really quite impressive. This could make for some quite fun summer afternoons, I think. With something like this, it obviously makes sense, not really to do it solo, but to do it as a community thing. So let's get some people round and have some fun. Come on, come on. Oh, no. Come on, come on. Oh, no! Oh! Yeah. Having something like this around really is heaps of fun, and it's a project I'm likely going to get a lot of use out of, particularly as it works so well. One thing to note is that it's also well sealed against rain ingress for when the weather turns bad, and there's really no way for water to reach the electronics thanks to the radiator having been sealed around its perimeter before being mounted. The one thing that I don't like is the big black border around the screen itself, and this is actually a result of my cost-cutting measures in using a coffee table for this glass. However, if you were to bump up the cost just slightly, it's actually possible to order a custom-cut sheet of toughened glass that matches whatever screen size you're using exactly, and that eliminates this border and should make it look really modern, and is definitely something that I would do if I was to build this again. Now, on the topic of cost, the figure that this cost me isn't accurate, because on top of doing a lot of recycling, I actually had some of the more expensive components already, like the LED backlights. However, with this design, assuming you do plenty of recycling and find a good supplier that's cheap for the backlight, it should be possible to build it for about $250 to $350. And that might initially sound like a lot for a DIY project, but when you consider that buying a TV of equivalent brightness to this would set you back about $5,000, it starts to look a lot better value. And for that kind of cost, you have to really want to use a TV outdoors to warrant it. However, with this, even if you only use it a few times a year, it more than pays for itself because of all the fun you'll have with friends watching sports or playing games outside whilst enjoying the summer. And that's really what this project is all about. So I hope you guys have enjoyed seeing how to make a super bright outdoor TV. I know it's not perfect, but it is essentially a prototype, and I think it works surprisingly well, all things considered, and you can make your own modifications if you ever attempt this thing yourself. Now, don't forget to subscribe if you have enjoyed this video, and I hope I see you in my next project. Who knows what that will be at this point. But other than that, I'm Matt, you've been watching DIY Perks, and I hope I'll see you next time. Goodbye for now.